Yes, so I'm Pieter Kok. I flew in from Sheffield, United Kingdom, to be here, and it's fantastic. We did this more than a year ago online, and we said, no, we need to do something in person. And here we are. So thank you to the organizers, Wang and Mark and everybody else whose names I kind of don't have ready right now. I want to talk about quantum imaging, something that was close to John's heart. In fact, he pretty much started it. We've already seen some of that. But before I do, I want to bring up this gentleman over here. He's been very important to my career progression because John was writing my letters of reference, and he shared it with me at one point, and I was very amused and horrified at equal measure that he told people, the interview panel, to ask me to pronounce this guy's name. So who is this? This is, what? What did I hear? So John said, and when he tells you, you'll have spit all over you. Because his name is Christian Huygens. And it's very difficult to pronounce for non-Dutch speakers. The Scots can do it, by the way. But that's another story altogether. Anyway, personal hero, a little bit, yes. On a par with Newton, that tells you something. So what I want to talk about today is I want to start with a little bit of John's legacy. So it says John's legacy, but it's going to be a tiny part, and how I fitted in there and how I came to know John. And then I want to talk about quantum imaging as a type of metrology where there's two aspects of it: noise reduction in your measurements and super resolution. So those are two different things. And then I'll offer some conclusions in the end. Much of the groundwork has already been laid by the fantastic talks that we heard from Irina and Paul. So thank you for that. That makes my work a lot easier. So, but of course, we know John partly from the Noon States. Notice that I spell it differently. We had
it's spelled incorrectly.
We had a big clash on what the correct spelling is, and this is it. But of course, this is the paper, the quantum lithography paper, that I wasn't on initially. So John had this idea, and they did the calculations, and so Ageli, whom I never met, he was, I think, a placement student who was writing a lot of this up, and no doubt did calculations, but they got a referee report back saying, yeah, this is all very well, but what kind of interesting things can you print with that? And so John was at a conference where he met my PhD supervisor at the time, Sam Brownstein, that fella, and Sam said, oh, I've got a PhD student, I think this will be a good question for him. So I set to work, and then we basically ended up making this plot, and that went into the referee report, and off it went into PRL. So I was in the good graces with John way before we actually met. Yeah, I think that helped. So this is the idea of quantum lithography, that you have two modes counter-propagating. We'll make this angle sort of basically plot pi over 2, so we look at the grazing limit. We have some kind of phase shift that we can control. Now, if you use classical light and you work out what is the minimum feature size that you can sort of deposit on the substrate, you end up with lambda over 4 sine phi. But if you use quantum light, Noon states, then you end up with this extra factor of 1 over n. And that's basically, well, this is ancient history now, but what you could do is create like thinner and thinner lines. So you can see that your resolution actually improves as you go higher up. Now, there are some problems with this. It's very, very difficult to make Noon states. And so this is what I came up with using like a complicated version of quantum superposition of noon states, and I ended up with this this beastie here. And yeah, so that's how I got into John's good graces. He invited me to apply for an NSF fellowship to do a postdoc at JPL. And I thought like, oh yeah, but he wants me. So I wrote it, and I had no contingency plan. And only later did I find out that the success rate was actually not so high. So so I was very lucky in that regard. Now, then there was some, it immediately triggered some early experiments. Jan Marchi with Milena D'Angelo and Maria Chikova. Of course, you know, all very active in the field. Still, there was the experiment by Bob Boyd, and then there were the noon state demonstrations. So there was the again, these people all have jobs in academia. So this was really a very fruitful fruitful area. Same thing here. And so I think he still has a job. So it led to a lot of really interesting experiments. Now, of course, it's really hard to make noon states, and they are incredibly fragile. So we've not really gone so much further in this direction, and probably nor do we want to, because the noise is just going to kill you. But it had a big impact. I would say it's one of the poster children, maybe not the poster child, for quantum technology that's not just key distribution or computing. This was before boson sampling, remember? Yeah, it's really difficult to implement in practice, but it really does tell you that you need to manage your noise very carefully. And then, finally, it's a really good stretch goal, and you need that if you want to write visionary ground applications. So, you know, how can we create these noon states? Well, that's when I came to JPL and started working with Wang and John, and so we had, and Nicholas Cerf was visiting at the time, so we came up with the first idea, and then another idea, and then came the Rosetta Stone paper. And this is where the infamous noon came in, where John, in the proofs, wanted to emphasize that these should be zeros, not O's, and so he put like a little, it's like matrix dot printer slash through, and of course the typesetters thought he meant phi, and this is how, in the very first, in-print definition of noon state, there's actually a typo. But there is another famous typo at a definition, and that's namely when Max Born introduced the interpretation of the well, the Born rule, probabilities, that the wave function is a probability amplitude. The typo there was that he didn't put the square in. So, you know, we're in good company.
That was not a typo, that was a thinko.
Oh, really? Oh, right, okay. Cool, all right, so thank you for that. Right, so, and then we had to come up, well, so I think we were referring to these as noon states because, well, n0 plus 0 n states is just too long when you're, you know, using them in anger. And so we refer to them as noon states, and then John was like, no, but these have to be, you know, high photon numbers because we need them to be really big. And so of course I couldn't find the original slide, but John came up with this slide, the high noon slide for the noon states. So I think this basically almost sums up John, because, you know, he had the guts to put this out up in front of the funding agents and whatnot. So, so yeah, so that's a bit of prehistory, and so now I want to sort of move to the slightly more technical and more current part of the talk. So imaging as a metrology problem, and so actually I'm going to move away from noon states altogether, and what I want to talk about is when we have an imaging problem where we have like a remote object that is emitting thermal light. So some black body, a star, whatever. And because we have thought a lot about what you can do with entangled light, with ghost imaging and quantum LiDAR and that sort of thing. And there you really have to engineer what your state of light is. But there's a whole host of applications where you have no control over the light that comes in, and you want to get the most out of your measurement procedure. Right? And in fact, today, a new black hole image was published of the supermassive black hole at the center of our Milky Way. And it looks very similar to the one that was published a couple of years ago. So that tells you that, you know, I think they know what they're doing. But what we wanted to look at here, and so this is work that I did with my colleague and my postdoc, we wanted to know, okay, when you get the light from like a distant star, what is the maximum amount of information about maybe the radius of this star? How can you get that? And so it's not so trivial actually, because we're not talking about measuring qubits. We have a light field, a field of electromagnetic radiation. So we wanted to have two detectors. And then what you have to do is you have to be very careful about the time that it takes to take your detection, so that you actually have a volume of the radiation field. And then you want to know how much information about the size and the shape of this object is in that amount of light, because that's what you capture, and that's what you want to maximally exploit. So that's what I just said. So what we can do is we can calculate so-called quantum fissure information for that light. And again, that wasn't so trivial, but we managed to do it. Well, Mark Peers, my postdoc, managed to do it. And here's another one, Van Zittert-Zernike. Van Zittert was, well, they were both working in the 30s, and they came up with a theorem that relates the coherence function of the light field in the image plane to the source distribution in the in the source plane. So here you have the source distribution, and then you can see that R1 and R2 are the points over here and over there. And so gamma here is the complex degree of coherence. And so if you know the complex degree of coherence, I think we need another acronym here, for every pair of points in your image plane, then you can reconstruct through the inverse Fourier transform, you can reconstruct what your source looks like. So that's in a nutshell what Van Zittert-Zernike says. And so the idea of this sort of imaging problem here now turns into having a single mode detector over here and a single mode detector over there. And then we can move the detectors around, and then we can get like the full picture of the entire image plane. And so what we want to do is we want to estimate the complex degree of coherence at the best possible precision. And so what do we find? We find that we have this general setup, because these are single mode detectors. This is the most general thing you can do in a unitary way. So we have some kind of phase shift that we have to determine how we need to set that. And then we have a beam splitter with some kind of transmission coefficient. And so the optimal phase setting here is actually equal to the phase of the complex degree of coherence that we want to estimate. So that's not going to do any good, because if we already knew it, we didn't have to measure it. And so we have to come up with some kind of adaptive setup. And that's a bit of a pain from a theoretical point of view. It's something I'd rather not do. So let's instead use just some random parameters and see how that works. And again, this was Mark Pearce's idea, because he was also daunted by the having to do an adaptive analysis. And so he chucked in random numbers. And what you see is that this is the ratio between the Fisher information for the actual information that you get out against the quantum Fisher information, which is the maximum information that is in there. And so it stays 1 for very, very long, and this is the magnitude of the complex degree of coherence. So it stays really, really high, and then it drops off a cliff. And so when we saw this, we thought like, well, now we're in business, so now we don't have to do any adaptive stuff. We just, as we take our data, we just, you know, mess with the phases, and in a random way. And then we collaborated with Andrew White's group, who actually could implement this with a laser. We wanted a black body source, so the way to do that is with a spinning glass disc that is sanded essentially, and so you get you destroy the phase information, and it becomes pseudo-thermal. Pseudo, I guess, because it's like a really pure single mode. But then the applied phase shift here is just basically a piece of glass that you slightly rotate, so you get different path lengths through your glass, and then you can basically do the entire range from 0 to 2 pi. And then there was a fiber coupled beam splitter and some fantastic transition edge sensing photodetectors that could do photon counting. All right, so so Lewis Howard and
Jeff Gillette
did the experiment, and so it's a little bit vague, but you can see the, so this picture here is the magnitude of the complex degree of coherence, and this picture here is the phase. And you can see the faint pink is the traditional, sort of like if you had to just put a lens with the same aperture as the distance between the two detectors. So if you do that, you get massive error bars, and your value is roughly here. So you've got a systematic error in there, and massive errors, stochastic errors. And when you do it with the near optimal system, you get much tinier error bars. And so this massively outperforms the traditional way. Same thing here, but this is for the phase. Maybe slightly less pronounced in terms of the improvement that you get in the errors, but a big difference nonetheless. Right. So now this is all well and good, and it looks fancy at a physics conference, but we also wanted a little bit more direct feeling for how good this is. So I think I wanted to show this. This is Andrew's joke, but at a memorial conference dedicated to Jonathan Dowling, this cannot, because this is a picture of Dorian Gray. And so we had a 100 by 100 pixel image, and then we simulated, so this is a simulation, a 26 by 26 array, and we basically took the noise data that we measured, and we put that in the theoretical model for how we would reproduce the image from this source material. And so this is if you have no noise and you take a 100 by 100 pixel image and you reproduce it with a 26 by 26 pixel. So you basically lose information, as you of course. And then if you do it the traditional way, you get this. And if you do it our way, the better way, you get this. But you also, so you see there's less noise here compared to there, but you also see that you don't get a resolution improvement, right? So what you get here really is a noise improvement. So I think that's an important distinction to make. Right, so then I started thinking, okay, what kind of really fancy tool can we make with this? And so I stole this picture of the internet, and I completely relabeled everything. So if you actually know what this means, then I apologize. The idea is that we have a CCD camera, right? And we want to do correlation measurements between different pixels. We need a beam splitter, but we can just use a lens for this because it's essentially a Fourier transform that we need to do. And then we can use a random phase mask. And the first time I showed this picture, somebody came up to me afterwards and said, "Oh yeah, you said that it was really difficult to maybe make a random phase mask, but you can buy them. They're stochastic light field modulators." So for the experimentalists in the audience, that's what I need. But you may require some substantial data processing because you get a lot of data, because you're looking at not at individual intensities on the CCD camera, but you're looking at all pairs, so it scales quadratically. All right, so now I want to look at the other case where we look at super resolution. I don't know how I'm doing for time. What's the
Should start coming to an end slowly.
Okay, so I'll come to an end really quick. Well, you know about finite resolution, the upper limit. I'll skip through this. There was a really nice paper by Nair and Zhang in 2016 that showed you can, in principle, get unlimited precision, right, resolution. So these two image sources can be arbitrarily close to each other, and you can still resolve them using SPADE, a quantum trick. The reason for that is that if you develop the wave function in terms of S to first order, then you get the derivative, and if these are Gaussians, then you basically end up with orthogonal Hermite-Gaussian modes, and you can measure those very precisely. All right, so now, is that true for any real objects? Unfortunately not. Because the two sources have to be exactly equal in size. And so here's the direct imaging. So this is like what Abbe would calculate. And this is the Nair and Zhang for perfectly identical sources, but some distance apart. And here is if one is almost 10 times brighter than the other, and you see you still get a much better performance than the direct imaging, which is over here. And so so then we started thinking about, okay, can you do this in sort of 3D? Can you do something more interesting, sort of more general? And so we considered if you have n weak incoherent emitters, like a star cluster, then and you've got m light collection positions, and then you send it through an interferometer R, then do photon counting. What can you do? And so what we found is that you can actually, with this setup here, you can saturate the quantum Fisher information of the light that comes your way. Right? So it means that I don't need any fancy entanglement to measure the light that's coming from here. I can use photon counting and passive linear optics. Okay, so yeah, so I'm just going to skip through this. So I've got two conclusions for this. So measuring the spatial property of a set of thermal light sources, you can do that optimally by linear optical interferometry. I think that's a big deal because it's quite accessible. And secondly, it beats the Abbe limit and is therefore proper super resolution. Or maybe you don't like that and you call this the new Abbe limit. I don't really care, but that's semantics anyway. Then, real quick, what happens if you do Hamburg-Brown twist? And so I think this is, I'll skip very quickly. So we can achieve really large baselines, right? So we can get like really large systems. However, you require photon coincidences, and they become exceedingly scarce if you use thermal light. And so we did the analysis. Okay, when do you want to use Hamburg-Brown twist, and when do you want to use the telescopes? So first order interferometry. And so here we have the precision on the vertical axis and the distance between two objects, and on the horizontal axis. And the blue line is the Hamburg-Brown twist. And you see it starts much lower, right? So if you have a lot of light, use interferometry, right? First order interferometry. But if you if they're really close together, your two sources, then this is for various differences in brightness. There is a plateau here where your Hamburg-Brown twist will outperform by quite some way. right? So you can't really see you can see a little bit the scale. So you can get an order of magnitude improvement, right? Which is a big deal. So the other lines is the extremely large telescope, and there's various other, and there's the very large telescope, there's Chara. So there's a lot of things went into this. So and it was just published in New Journal of Physics. And then the last thing that I want to highlight is an experiment where we wanted to see how can we tell that we have one or two sources, which is of course very important for exoplanet detection. And so one of them may be much weaker than the other. And so for this we didn't use the quantum Fisher information but the quantum relative entropy. And so this is the experimental setup, and we had a fantastic experimental team from Harriet Watt in Edinburgh. And they had an optical feedback control loop in there to get everything stabilized. And so the idea here is, so this is the relative entropy. So so you want to be high, and this is the theoretical limit. So this is basically saying how well you can determine the difference between the two situations, the two hypotheses. And so the crosses here is the experimental data. And then when we take into account the visibility of the experiment and model that in there as well, then we get the dotted line, so it lies really perfectly on there. So the visibility is really your limiting factor there. And then the other thing was looking at the mean square error of the separation between the two. And again, this is the direct imaging limit. This is the Fisher information, the quantum Fisher information, so this is the quantum limit, and then again we lie really low. And this one here is part of the legend, so this is not in outline. I felt it was important to mention. Now, okay, so some conclusions. I think by considering the information about a physical system, physical quantity, that we can extract in a quantum measurement, we can design the optimal imaging systems. I think this is quite a big deal. There's no more, you don't have to try any harder because there's nothing more in it. We can reduce the noise, as you've seen, and we can also increase the resolution compared to direct imaging, for which the traditional upper limit holds. And that's true even when the incoming light is purely classical, which I find very fascinating. Okay, so, experiments, some experimentalists gathered here demonstrate that this is indeed feasible technology. All right, so I promised I was going to say a little bit about the special memorial issue for Jonathan Dowling. So I'm the associate editor for AVS Quantum Science. It is a journal from the American Institute of Physics, which when they invited me, we all get these invitations, but when I saw it was AIP, I thought, okay, this is legit. And so we started a couple of years ago, and it's been growing very steadily. And so I've already put most of your names on the list, so you'll be getting emails asking you to contribute. And so hopefully we can make this happen. We will make it happen, and hopefully you can be part of it. So the publishing date will be sometime in May 2023, but we like to liaise with our authors so that we know what's in the pipeline, and you know that you're being supported throughout. And so submissions start today, I guess. So if you have any questions, please contact me. My co-editor is Xijin Wang, who also worked with John, and she's in Sydney right now. And with that, I would like to thank you very much.
Thank you, Peter. We still have time for a couple of questions before coffee.
How do I understand why the random faces work?
Because I kind
In
of
the beginning with the fence.
because I kind of glossed over this a little bit. So my postdoc thought, like, let's chuck some random phases at it, and then and so that was a really inspired move because it gave a fantastic result. And then the experimentalists got their hands on it, and they go like, random phases, that's a pain in the ass. Let's just rotate this thing one step at a time. So you basically, well, it's not the randomness that is important. What is important is that you scan through the whole thing, and then and then you get something that is near optimal. So you basically want to sample the entire phase, and then of course you can narrow down if you so wish.
Great. Anybody else? Thanks, Peter, and thanks for doing the special issue. That's very
Yeah,
important.
well-
Thank you very much. Coffee time!